In computer science, arbitrary precision arithmetic, also called bignum arithmetic, multiple precision arithmetic, or sometimes infinite precision arithmetic, indicates that calculations are performed on numbers whose digits of precision are limited only by the available memory of the host system. This contrasts with the faster, fixed precision arithmetic found in most arithmetic logic unit hardware, which typically offers between 8 and 64 bits of precision. Several modern programming languages have built-in support for bignums, and others have libraries available for arbitrary precision integer and floating point math, rather than store values as a fixed number of binary bits related to the size of the processor register. These implementations typically use variable length arrays of digits. Arbitrary precision is used in applications where the speed of arithmetic is not a limiting factor, or where precise results with very large numbers are required. It should not be confused with the symbolic computation provided by many computer algebra systems, which represent numbers by expressions such as pi/sin, and can thus represent any computable number with infinite precision. Applications. A common application is public key cryptography, whose algorithms commonly employ arithmetic with integers having hundreds of digits. Another is in situations where artificial limits and overflows would be inappropriate. It is also useful for checking the results of fixed precision calculations, and for determining the optimum value for coefficients needed in formulae, for example the square root of 1/3 that appears in Gaussian integration. Arbitrary precision arithmetic is also used to compute fundamental mathematical constants such as pi to millions or more digits, and to analyze the properties of the digit strings, or more generally to investigate the precise behavior of functions such as the Riemann zeta function, where certain questions are difficult to explore via analytical methods. Another example is in rendering fractal images with an extremely high magnification, such as those found in the Mandelbrot set. Arbitrary precision arithmetic can also be used to avoid overflow, which is an inherent limitation of fixed precision arithmetic, similar to a 5-digit odometer's display which changes from 99,999 to 00000. A fixed precision integer may exhibit wraparound if numbers grow too large to represent at the fixed level of precision. Some processes can instead deal with overflow by saturation, which means that if a result would be unrepresentable, it is replaced with the nearest representable value. Some processes can generate an exception if an arithmetic result exceeds the available precision. Where necessary, the exception can be caught and recovered from. For instance, the operation could be restarted in software using arbitrary precision arithmetic. In many cases, the programmer can guarantee that the integer values in a specific application will not grow large enough to cause an overflow. However, as time passes and conditions change, the bounds of the guarantee can be exceeded. For example, implementations of the binary search method that employ the form the 2nd of May function incorrectly when the sum of L and R exceeds the machine word size, although the individual variables themselves remain valid. Some programming languages such as Lisp, Python, Perl, Haskell and Ruby use, or have an option to use, arbitrary precision numbers for all integer arithmetic. Although this reduces performance, it eliminates the possibility of incorrect results due to simple overflow. It also makes it possible to guarantee that arithmetic results will be the same on all machines, regardless of any particular machine's word size. The exclusive use of arbitrary precision numbers in a programming language also simplifies the language, because a number is a number and there is no need for multiple types to represent different levels of precision. Implementation issues. Arbitrary precision arithmetic is considerably slower than arithmetic using numbers that fit entirely within processor registers. since the latter are usually implemented in hardware arithmetic whereas the former must be implemented in software. Even if the computer lacks hardware for certain operations and software is provided instead, it will use number sizes closely related to the available hardware registers. 1 or 2 words only and definitely not n words. There are exceptions, as certain variable word length machines of the 1950s and 1960s, notably the IBM 1620, IBM 1401, and the Honeywell Liberator series, could manipulate numbers bound only by available storage with an extra bit that delimited the value. Numbers can be stored in a fixed point format, or in a floating point format as a significant multiplied by an arbitrary exponent. However, since division almost immediately introduces infinitely repeating sequences of digits, should this possibility arise, then either the representation would be truncated at some satisfactory size or else rational numbers would be used. A large integer for the numerator and for the denominator. But even with the greatest common divisor divided out, arithmetic with rational numbers can become unwieldy very swiftly. 1/99th to 1/100th equals 1/9900th, and if 1/101st is then added, the result is 10,999,900ths. The size of arbitrary precision numbers is limited in practice by the total storage available, the variables used to index the digit strings, and computation time. A 32-bit operating system may limit available storage to less than 4 gigabytes. A programming language using 32-bit integers can only index 4 gigabytes. If multiplication is done with an O algorithm, it would take on the order of 10-12 steps to multiply 2 1,000,000 word numbers. Numerous algorithms have been developed to efficiently perform arithmetic operations on numbers stored with arbitrary precision. In particular, supposing that n digits are employed, algorithms have been designed to minimize the asymptotic complexity for large n. The simplest algorithms are for addition and subtraction, where one simply adds or subtracts the digits in sequence, carrying as necessary, which yields an O algorithm. Comparison is also very simple. Compare the high-order digits until a difference is found. Comparing the rest of the digits, words, is not necessary. The worst case is O, but usually it will go much faster. For multiplication, the most straightforward algorithms used for multiplying numbers by hand require O operations. But multiplication algorithms that achieve O-log complexity have been devised, such as the Schonage-Strassen algorithm, based on fast Fourier transforms. And there are also algorithms with slightly worse complexity but with sometimes superior real-world performance for smaller n. The Karatsuba multiplication is such an algorithm. For division, see division algorithm. For a list of algorithms along with complexity estimates, see computational complexity of mathematical operations. For examples in x86 assembly, see external links. Preset precision. In some languages such as REXX, the precision of all calculations must be set before doing a calculation. Other languages, such as Python and Ruby, extend the precision automatically to prevent overflow. Example: the calculation of factorials can easily produce very large numbers. This is not a problem for their usage in many formulae because they appear along with other terms, so that, given careful attention to the order of evaluation, intermediate calculation values are not troublesome. If approximate values of factorial numbers are desired, Stirling's approximation gives good results using floating-point arithmetic. The largest representable value for a fixed-size integer variable may be exceeded even for relatively small arguments, as shown in the table below. Even floating-point numbers are soon outranged, so it may help to recast the calculations in terms of the logarithm of the number. But if exact values for large factorials are desired, then special software is required, as in the pseudocode that follows. which implements the classic algorithm to calculate 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, etc. The successive factorial numbers. Constant limit equals 1000%, sufficient digits. Constant base equals 10%, the base of the simulated arithmetic. Constant factorial limit equals 365%, target number to solve 365. Array digit 1, limit of integer, percent the big number, integer carry, d, percent assistance during multiplication, integer last, I, percent indices to the big numbers digits. Array text 1, limit of character, percent scratchpad for the output. Constant t digit 0 to 9 of character equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Began digit equals 0%. Clear the whole array. Digit 1 equals 1%. The big number starts with 1. Last equals 1%. Its highest order digit is number 1. For n equals 1 to factorial limit 2% step through producing 1, 2, 3, 4, etc. Carry equals 0%. Start and multiply by n. For I equals 1 to last 2% step along every digit. D equals digit I asterisk n plus carry, percent the classic multiply. Digit I equals d mod base, percent the low order digit of the result. Carry equals d div base, percent the carry to the next digit. Next I, while carry greater than 0%, store the carry in the big number. If last greater than equals limit, then croak, percent if possible. Last equals last plus 1%, one more digit. Digit last equals carry mod base, percent placed. Carry equals carry div base, percent the carry reduced. When percent with n greater than base, may be greater than one digit extra. Text equals percent. Now prepare the output. For I equals 1 to last 2%, translate from binary to text. Text limit I plus 1 equals t digit I, percent reversing the order. Next I, percent Arabic numerals put the low order last. Print text equals n, percent print the result. Next n% onto the next factorial up. End. With the example in view, a number of details can be discussed. The most important is the choice of the representation of the big number. In this case, only integer values are required for digits, so an array of fixed-width integers is adequate. It is convenient to have successive elements of the array represent higher powers of the base. The second most important decision is in the choice of the base of arithmetic, here 10. There are many considerations. The scratchpad variable d must be able to hold the result of a single-digit multiply plus the carry from the prior digit's multiply. In base 10, a 16-bit integer is certainly adequate as it allows up to 32,767. However, this example cheats, in that the value of n is not itself limited to a single digit. This has the consequence that the method will fail for n greater than 3,200 or so. In a more general implementation, n would also use a multi-digit representation. A second consequence of the shortcut is that after the multi-digit multiply has been completed, the last value of carry may need to be carried into multiple higher-order digits, not just one. There is also the issue of printing the result in base 10 for human consideration. Because the base is already 10, the result could be shown simply by printing the successive digits of array digit, but they would appear with the highest order digit last. The whole array could be printed in reverse order, but that would present the number with leading zeros which may not be appreciated. So we decided to build the representation in a space-padded text variable and then print that. The first few results are, we could try to use the available arithmetic of the computer more efficiently. A simple escalation would be to use base 100, or, with sufficiently wide computer variables we could use larger bases, such as 10,000. Working in a power of 2 base closer to the computer's built-in integer operations offers advantages, although conversion to a decimal base for output becomes more difficult. On typical modern computers, additions and multiplications take constant time independent of the values of the operands, so there are large gains in packing as much of a big number as possible into each element of the digit array. The computer may also offer facilities for splitting a product into a digit and carry without requiring the two operations of mod and div as in the example, and nearly all arithmetic units provide a carry flag which can be exploited in multiple precision addition and subtraction. This sort of detail is the grist of machine code programmers, and a suitable assembly language big number routine can run much faster than the result of the compilation of a high-level language, which does not provide access to such facilities. For a single digit multiply, the working variables must be able to hold the value squared plus carry, where the maximum value of the carry is. Similarly, the variables used to index the digit array are themselves limited in width. A simple way to extend the indices would be to deal with the big numbers digits in blocks of some convenient size so that the addressing would be via, where I and j would be small integers. Or, one could escalate to employing big number techniques for the indexing variables. Ultimately, machine storage capacity and execution time impose limits on the problem size. History. IBM's first business computer, the IBM 702 of the mid-1950s, implemented integer arithmetic entirely in hardware on digit strings of any length from 1 to 511 digits. The earliest widespread software implementation of arbitrary precision arithmetic was probably that in MacLisp. Later, around 1980, the operating systems VAX, VMS and CMS offered bignum facilities as a collection of string functions in the one case and in the languages exec2 and rexx in the other. An early widespread implementation was available via the IBM 1620 of 1959 to 1970. The 1620 was a decimal digit machine which used discrete transistors. Yet it had hardware to perform integer arithmetic on digit strings of a length that could be from 2 to whatever memory was available. For floating-point arithmetic, the mantissa was restricted to 100 digits or fewer, and the exponent was restricted to 2 digits only. The largest memory supplied offered 60,000 digits. However, Fortran compilers for the 1620 settled on fixed sizes such as 10. Though it could be specified on a control card if the default was not satisfactory. Software libraries. Arbitrary precision arithmetic in most computer software is implemented by calling an external library that provides data types and subroutines to store numbers with the requested precision and to perform computations. Different libraries have different ways of representing arbitrary precision numbers. Some libraries work only with integer numbers. Others store floating-point numbers in a variety of bases, rather than representing a number as single value. Some store numbers as a numerator-denominator pair, and some can fully represent computable numbers, though only up to some storage limit. Fundamentally, Turing machines cannot represent all real numbers, as the cardinality of exceeds the cardinality of.